Welcome to this video. Today we are discussing machine learning opportunities in power systems from an academic perspective. After today's lecture, you should be able to identify possible applications of machine learning in future power systems. As you know, the future power system is intelligent. This means that the system is being expanded with new devices that are intelligent and communicate with each other, such as electric vehicles, dishwashers, or other types of equipment. Intelligence is not only being added to the residential side, but also in industry. This means that the improved control devices and communication also enables the industry to participate, for instance, in demand response programs. So the entire system is now being expanded with flexibility on both the residential and the industrial sides. At the same time, the grid becomes more observable through measurements because more data is collected locally and in the control room. This enables us to better understand machine learning opportunities, either on the edge of the grid or centralized in the control room of the system operator. The opportunity for all participants is to understand this new type of data and apply adequate machine learning methods to balance and intelligently control the power system. However, some challenges come with that. Physics is non-debatable, and the power system is a physical grid. So not all possibilities that machine learning suggests or predicts may be possible in the real grid. For instance, the power balance must be matched at all times. So suggested control actions by a machine learning tool need to be verified that they satisfy this law. So this means that machine learning models need to either learn to respect the physics or need to be limited implicitly by the physical feasibility of the system operation. At the same time, a second challenge is the human-machine interaction. Human-machine interaction happens either on the end-user side or inside the control room of system operators. The latter are experts on the subject. And machine learning is known to be biased, which does not meet our societal standards of being fair and trust-based. So the challenge is, how can machine learning models and human interaction be designed for overall power system objective, while also be ethically responsible. Finally, when we introduce more interconnectivity and machine learning in the power system, it will raise the threat to cyber insecurities. This means that hackers may try to attack the power system to manipulate the system operations for their own strategic goals. Therefore, cybersecurity needs to be at all times in our minds when we design new machine learning models and tools. As these three topics are so important, let us go through them in more detail. Physics-based models are machine learning models that need to respect physics. So how can we integrate physics-based models with machine learning methods to make the best use of both worlds? The physics equation-based models are models where we know equations such as the energy conservation. But perhaps we can also use those equations to enhance and support the learning from data. For instance, those equations could be used for regularization the model to add information and improve an ill-posed learning problem and avoid overfitting. So the challenge is, how can we use those physical equations to regularize and train the model most effectively such that it knows where to search for and what kind of data to use? One challenge in terms of the human interaction is that these machine learning models need to be understandable by humans. Otherwise, they cannot be used. For instance, an expert, system operators, is a safety critical task, and without understanding machine learning assistance, it is tough for engineers to build up this trust. Also, when humans use machines to assist them in making decisions and observing the grid, building up trust is very important. Finally, a challenge in human-machine interaction, unique for power system and energy machine learning methods, is that the solution need to be non-intrusive. This means not to disturb and respect the discomfort and privacy of humans as end users of the energy system. This is then how machine-human interactions should be for energy systems. The third challenge is cybersecurity. There may be someone who has strategic intention to attack the energy system to either observe data for analysis or manipulate the operation to create partial blackouts or other catastrophic events. Such a hacker can use techniques as already used on the internet. So if the power system is now intelligent and digital, data can be more easily manipulated. This is already an existing threat, for instance, in the United States. Approaches are already investigated, such as reinforcement learning, to realize sequential decision-making with safety in mind. Those models are then used for real-time operation purposes. To recap, power systems are becoming more intelligent and digital, and more data is being collected. Machine learning models powered by this data have the opportunity to support system operations at different locations, ranging from the generator side to the industry side and inside the control room of the system operator. However, there are three main challenges. Firstly, the physical relationships of the power system are non-debatable. So this means that physics need to be respected at all times. Regularization and the inclusion of physics-based methods are crucial when moving towards machine learning opportunities. Secondly, human interaction will change how we, or system operators as experts, interface with these assistants and machine learning-based agents. Finally, cybersecurity is vital to ensure that the new methods are securely designed and that they can be used in real time. Thanks for joining us today.